Let's continue working with our kinematics equations and progress through some more example problems, perhaps with a little bit increasing level of difficulty. So a reminder of the kinematics equations. At this point, you probably are starting to memorize these. So distance is equal to average velocity multiplied by time. Final velocity equals initial velocity plus the product of acceleration and time. Distance can also be found by multiplying initial speed and time and adding to it another term that has to do with acceleration and time, actually time squared. Final velocity when squared equals initial velocity squared plus the product of 2 times the acceleration times the displacement. Okay, a key to all these equations that was stated earlier, but I don't want you to forget, is these equations are only valid if acceleration is constant or uniform. That's because this expression is really an expression for average velocity, but we can only compute average velocity by taking half of the sum of the initial and final values in the case where acceleration is uniform. And because these other equations depended on substitutions into this first equation, then they all rely on this condition. Okay, so some of the tips. Spend more time setting up the problem than solving the problem. Show all the steps of your algebra. Make lists of what's known and unknown. Convert your units correctly, so on and so forth. Let's see if we can apply the problem-solving approach to the case of a motorcycle that goes from one stoplight to the next as it drives through city traffic. So the motorcycle moves forward as a stoplight turns from red to green. The first 75 meters are covered with a uniform acceleration of 6 meters per second squared. And then the motorcycle stops accelerating, and for a while it maintains constant speed for 450 meters. And then it comes up to the next stoplight that's red, and so the motorcycle has to decelerate. It spends 4 seconds doing so, and then comes to rest. So now we have a multiple part problem here. We got to answer questions A through F. The first one asks for us to sketch the graph of the motion on a velocity versus time graph. So before we finish this graph, let's just make a little sketch of what's going on here. Let's see. All right, so there's a stoplight. It's just turned from red to green, and the motorcycle progresses down the x-axis. For the first interval, it has some positive acceleration. Then in the second interval, the acceleration is 0, meaning it maintains constant velocity. And then in the third interval, it approaches the next traffic light, and it has some negative acceleration. So velocity versus time graph. We know it starts out with a velocity of 0, right, when this light first turns green. And because it's accelerating, its velocity is gradually increasing. But because it's a uniform acceleration, that increase appears as a straight line segment on our velocity versus time graph. Whatever velocity it reaches, it then maintains, and then it has to decelerate back to rest. Okay, so we have intervals 1, 2, and 3 that correspond to the intervals described in our motion diagram. Okay, and that's as much as we can do. Now, ultimately, we're going to want to figure out some of these values, right? We want to know what is that velocity that it maintains in interval number 2, and we need to know how much time did it take before it got to the end of the first interval or the end of the second interval and so on. Okay, question B. What total distance does the motorcycle travel? Now, our kinematics equations are only valid if acceleration is constant. Well, the acceleration isn't constant. It has a different acceleration here, right? A positive acceleration. It has 0 acceleration in this interval, and then it has a negative acceleration for this interval. But I can take it piecewise, and just within this interval, the acceleration is uniform. So I can solve for motion using kinematics equations during interval number 1, and then I have to solve a separate problem for interval number 2, and so on. So let's make the typical list that we have: displacement, time, initial velocity, final velocity, and acceleration, and then let's graphically organize and see if we can identify what these quantities are in each of the 3 intervals as a separate problem. So we are clearly spending more time setting up the problem than solving it by putting a motion diagram along with a graph and a graphic organizer. So we're going to have to refer back to the problem a couple times and reread it, but let's see how much information we can put in here. So in interval number 1, we know that the distance traveled is 75 meters, and we know the acceleration is positive 6 meters per second squared. We know the initial velocity is equal to 0, and if we want to know how much time is spent at that interval, we can choose one equation. If we want to know what the final velocity is, we can choose a different one. Let's try this first. Let's figure out what the final velocity is. So there's an equation that doesn't involve time. So let's ignore time for right now. What's the kinematics equation that doesn't have t anywhere in it? I'll give you a second to look through the kinematics equations or see if you know it off the top of your head. Normally I would write all 4 of them down, and that would be my advice to you. If you're not sure which one, just see if you can write all 4 of them, and then by investigating them, which is the one that doesn't include t. So you've probably figured out by now it's the equation that says v squared equals v naught squared plus 2a delta x. Now, at this point, it's very easy algebra to isolate. For v, we just need to take the square root of both sides of the equation. So v equals the square root of v naught squared plus 2a delta x. And now we can plug in the numbers and the units. So v is equal to the square root of, this is easy, 0 squared plus 2 times 6 meters per second squared times 75 meters. Oops, I left out the units. Okay, so before we even do the numbers, let's just look at the units. A meter times a meter per second squared gives you a meter squared per second squared, but we are taking the square root of all of this, so that would give you meters per second, which is exactly what we expect. So we verified that the equation is dimensionally correct. 2 times 75 would be 150, and 6 times 150 is the same thing as 6 times 100 plus 6 times 50, so this is 600 plus 300. Okay, so if you want to use a calculator, you can. If not, this is mental math, I believe. We're talking about the square root of 900, which is 30, right? So, oops. We get an answer of 30 meters per second as the velocity at the end of interval number 1. That means that's the initial velocity at the beginning of interval number 2, as well as the final velocity at the end of interval number 2, because in interval 2 it's maintaining constant velocity. We're also told in interval number 2 that the distance traveled is 450 meters. We know the acceleration is 0. That's implied by saying it's constant velocity. So we just need to figure out the time in interval number 2. Well, that's easy. 450 meters at a constant speed of 30 meters per second. Meters cancel. It's the inverse of seconds. We can knock off a 0. 45 divided by 3 is 15. So 15 seconds in the second interval of motion. Now, in the third interval of motion, it enters into that part also with an initial speed of 30 meters per second, but we know the final speed is 0 because it comes to rest. We're also told that the deceleration lasts for 4 seconds. And that's as much as we're given for the final interval. So let's see if we can figure out what the acceleration value is in the last interval. So for now, we're ignoring the distance traveled in the final interval. And so the equation that leaves out distance is the kinematics equation. See if you know it. Right? Isn't it the one that says V equals, what is it? V naught plus AT. Wait, is that AT squared or is that AT? Well, I think you've got it right. It's AT. However, I could imagine a case where you might get confused with these equations and perhaps memorize it incorrectly and think this is a t squared. However, when you go to solve the problem with an incorrect equation and you have a quantity that's squared that shouldn't be, then the units aren't going to work out and you'll catch yourself as long as you're taking my advice of plugging the units in with the numbers. So you can avoid mistakes by double checking for dimensional correctness. Anyway, if we're trying to find the acceleration, then we need to do the algebra. So step 1, step 2, AT equals V minus V naught. Step 3, A equals V naught minus V divided by T. So this is equal to 0 meters per second minus 30 meters per second divided by 4 seconds, which gives us an acceleration of negative 7.5, and then the units are meters per second, or meters per second squared. Now the negative means that the force of friction that slows the motorcycle down is a force that doesn't point forward in the positive x-axis. The force of friction between the wheels and the motorcycle points back in the negative direction. Okay, so what total amount of time is the motorcycle in motion? Oh, well, it's 4 seconds plus 15 seconds plus, and now we need to figure this out. Well, in this case, we can use any equation that involves time. And we might as well use the equation we just used for our last problem. So if you work the algebra, time is equal to V minus V naught divided by A. So in the first interval, that would be 30 minus 0 divided by 6. 30 meters per second minus 0 meters per second divided by positive 6 meters per second squared. Dimensionally, you see that this works out to give units of seconds, and the answer is 5. So a grand total of 24 seconds were spent moving from one stoplight to the next. Oh, that was the answer to part C. My bad. Part B was what was the total distance. Oh, the total distance is 75 meters plus 450 meters plus, oops, we ignored this initially. Now we need to figure out what was the distance traveled in interval number 3. So we can use one of two equations for that. The equation delta x equals 1/2 V naught plus V times T, or just as well, we could say delta x equals initial velocity times time plus 1/2 acceleration times time squared. Let's go with this one. So the distance traveled in interval number 3 is 1/2 times 30 meters per second plus 0 meters per second times 4 seconds. So delta x is equal to 15 meters per second times 4 seconds. Seconds cancel out, and we get 60 meters. So 450 plus 60 would be 510, plus 75 would be 585 meters. How does the motorcycle's deceleration compare to its acceleration? Well, the deceleration is a negative value versus the acceleration is a positive value. How about the magnitudes? The positive acceleration is 6, the negative deceleration is 7.5, so it's greater in magnitude. Let's see, did we graph it correctly? Oh, I must have known what I was doing, because if you take a close look at the graph, I made the slope that would correspond to the acceleration in interval number 1 not quite as steep as the negative slope portion of the graph. So I think I got lucky. What does the slope of the graph indicate? Acceleration. What does the area under the curve indicate? Well, the vertical scale is in units of meters per second, and the time axis, of course, is in seconds. So if we were to calculate an area, like this central rectangle of the area under the curve, we could get that by taking a length multiplied by a width, but that would just be multiplying units of meters per second times seconds, and a meter per second multiplied by a second leaves you with meters, so the area under the curve represents distance. Okay, so we can solve more challenging problems if we're willing to break the problem up into intervals and, along with our motion diagram, come up with some sort of graphic organizer of the information. And so you can see setting up the problem is really where most of the work is done. The solving of the problem generally involves very basic algebra and number crunching. So spend more time setting up the problem, solving the problem, and you'll be well on your way to applying kinematics equations successfully.